All right, so where we left off last time, we were talking about how the graph in the previous example, example 2, has a horizontal asymptote since the function values approach 0 as x increases without bound, so as x runs towards infinity, or as x decreases without bound. So that without bound means as x runs toward negative infinity. And so horizontal asymptotes occur because of the end behavior of a graph. And that's what we're going to talk about next. That's what the last bit of examples are. So the end behavior of a function, f of x, is the simplest function, g of x, whose graph looks very similar to f of x when x runs to positive infinity or runs to negative infinity. And what we say mathematically is G is the end behavior of f when, and this is something you'll see in calculus, so I'm just introducing it to you right now, when the limit as x goes to plus or minus infinity of f of x divided by g of x, when that limit is equal to 1. I don't expect that to make much sense right now, but here's the idea. So the end behavior model of f of x is x to the fourth plus x cubed plus x minus 20 is, well, which of these terms is making the biggest impact in terms of as x gets bigger and bigger and bigger or more and more negative? It's this leading term. So anytime you're looking at a polynomial, it's the leading term that's going to be your end behavior function. So let's just look at the graph of these two things. So let's add a graph. We'll let f1 be x to the fourth plus, oh, no, what happened? No! Plus, there we go, plus x to the third plus x minus 20. There we go. That's okay. And then let's also on the same grid graph our second one, just x to the fourth. And so that one's in red. So let me pull this up and let's see what we can see. So first of all, we can see that our first function that's blue, right around 0 and actually kind of in between like -3 and +3, they're very different. In fact, let's go ahead and change the window settings. Let's let the x-min be, I don't know, -30. We'll see if that gives us enough. Oh, no, let's change x from -3 to +3. That's what I said, from about -3 to +3. And the y-min, let's let that be -30 and see if that's enough. And yeah, so somewhere at maybe, 25 is where this kind of bottoms out here. So very different where x is kind of a small value. But let's now look at this same graph in a different window. If we, window settings, if we let x run from -60, we won't even go like a million billion, but let's just go -60 to +60. We'll leave the y-min at -30, and the y-max, whoops, don't know what happened there. I accidentally dragged it up. I didn't know I could do that. Let's let the y-max, just because x to the fourth grows really, really fast, we're just going to go 1, 2, 3, 4, 5, 6, a bunch of zeros. Okay? And lo and behold, yeah, as x runs, gets bigger and bigger and bigger, and x gets more and more negative, bigger negative, bigger negative. I mean, technically it's smaller and smaller, but when I think of smaller, smaller, I think fractions. So these two graphs are almost indiscernible as x goes to positive and negative infinity. So their end behavior, the end of the x-axis, right, is where they're the same. And in calculus, we'll see why that's true. Oh, I can't help. Sneak peek. I can't resist. Right, this is more info than you need. But if you were going to look at the limit as x runs to infinity of x to the fourth plus x cubed minus x minus 20, all divided by x to the fourth, you could break this into little tiny fractions and say, hey, well, that's the limit as x runs to infinity of x to the fourth over x to the fourth is 1, plus x to the third over x to the fourth simplifies to 1 over x, minus 1 over x cubed, minus 20 over x to the fourth, which I'm totally writing very sloppily and out of the page. I apologize. But just think about it. If x is getting really, really big, what is 1 over x becoming? Say x is 100. This is 1 over 100. If x is 1,000,000, this is 1 over 1,000,000. This little fraction here is basically going to 0. So is this little fraction. So is this little fraction. All these pieces go to 0. So my limit is going to equal just 1 plus 0 plus 0 plus 0 is 1. That's what it's talking about here. Okay. Total 100% that was calculus, because the foundation of calculus is limits. Sneak peek. I don't expect you to know how to do that right now, but I couldn't resist. So, okay, but because this whole, the limit needs to be 1, the leading coefficients matter as well. So in example 4 here, the end behavior of f of x is 0.01 x cubed plus 10 to the x squared plus 100x plus 9,999 is, again, you look at the leading term and you must also include the coefficient. So that if you were to take f of x and divide by g of x, you would have 0.01 divided by 0.01 would give you that limit equaling 1. So the leading coefficients matter. So with polynomials, you grab the leading term and its coefficient. For rational functions, right, this guy right here, the end behavior model of f of x equals x squared minus 2, all divided by x to the fourth plus x cubed plus x. So, sorry, I lost my thought there. The end behavior of this rational function, which I'm going to write as rational looking, so x squared minus 2 all over x to the fourth plus x cubed plus x. The end behavior function for this guy, similar to your polynomials, you're going to want to grab the leading term in the numerator and the leading term in the denominator, and let that be your g of x, right? So g of x is going to equal x squared over x to the fourth, and that just simplifies to 1 over x squared. So that's our end behavior function. All right, so now you try. Take what you just learned in the last 3 examples, and you try. What is the end behavior model? What function g of x will model the end behavior of this rational function of 5x cubed minus 2 all divided by 10x squared plus x plus 9. So go ahead and pause the video right now. Try that on your own. Alrighty, and this is the solutions that I wrote up before. For I probably shouldn't. I'm going to move this over here. Whoa, I'm moving. All right, so what's the end behavior? Again, take leading term up top, divide it by the leading term down below. These simplify to 1/2 x. Now, that's the equation of a line. And here's the interesting thing. Whenever your end behavior is linear, it's an asymptote. We call it an asymptote. So lines that are not horizontal, we call slant asymptotes. So again, if the end behavior is linear, we call it an asymptote. For these guys, the end behavior is polynomials or rational functions. We don't call those asymptotes. We only call linear end behavior asymptotes. And in this case, it's a slant asymptote. And I went ahead and graphed the two of them. And you can see as x gets bigger and bigger, or more and more negative, my function f approaches it. So let's go back to our worksheet and now look at last example, number 7. So before I look at the graph, let f of x be x cubed divided by 4 minus x squared. So determine the following characteristics of f of x. Go ahead, see if you remember some of this vocabulary from before, upper bound, lower bound, even, odd, or neither. And even, odd, or neither, show that algebraically. Determine that algebraically. So I'm going to pause again and give you a moment to try and do this on your own. Sorry, when I pause the video, that doesn't do anything. You need to pause the video and you need to try these problems on your own right now. You pause. And here we have it. All right, so when you're determining whether a function's even or odd, you start with f of negative x. And you'll remember if it's even, f of negative x is just equal to f of x, right? Even means it's symmetric about the y-axis. So positive x values and negative x values give you the exact same y value. If it's odd, f of negative x will equal negative f of x. The x and y values are opposite, or not opposite, they are 180-degree rotation of each other. So if x was positive, y would, never mind, I'm not going to say what I was about to say. So in this case, when we plug f of negative x in, it works out to being negative f of x. So that's an odd function. The domain and range, again, the domain, you want the denominator to not equal 0. So that's when x is plus or minus 2. So the domain is the set of all x values such that, that's tall line there means such that, x cannot equal positive or negative 2. And the range of this guy, I had to look at the graph, right? Just from the equation, the range might not be so obvious. So let's take a sneak peek right now at the graph down below. And yeah, we can clearly see from this part of the graph, the range is everything from negative infinity up to positive infinity. So bold R means all real numbers, or you could have written it in interval notation from negative infinity to positive infinity. Vertical and horizontal asymptotes. All right, the vertical asymptotes are where you've got zeros in your denominator that don't get canceled out, right? If they got canceled out, you'd have a hole. But in this case, you have two infinite discontinuities called vertical asymptotes, right, at x equals 2 and x equals negative 2, which again, you can see very nicely on your graph. Now, what I graphed in here is my end behavior. I'll come back to that. But there is no horizontal asymptotes. So a horizontal asymptote would have been a horizontal line that as x went to infinity or as x went to negative infinity, your graph would be approaching. So there were no horizontal asymptotes in this example. Upper bound, lower bound, none, because again, my range was all real numbers. There is no upper bound or lower bound for the entire graph. There are local max right around here, and there is a local minimum right around here, which again, I didn't bother finding because I didn't actually ask you. And being bounded is not the same thing as having a local min or local max. So in this case, upper bound or lower bound refers to the entire function. Local mins and local maxes refer to locally, just near the area. So again, the end behavior model, g of x, for this function, you're going to take the x cubed over negative x squared. Remember, the coefficients matter, so that's a negative x squared. And when you simplify that, you get a line, y equals negative x, right? Since the end behavior function is a line, it's an asymptote. We call it a slant asymptote. Some other textbooks call them oblique asymptotes. So you might occasionally run into that. And you can kind of see it beginning as x gets more and more negative, and as x gets more and more positive, you can see my blue function getting closer and closer to that slanted line. And that, ladies and gentlemen, will do it for 1.2 section B.